Hi, everyone. This is your People Behind the Science podcast host, Dr. Marie McNeely, and I'm excited to have you here with me for episode 802 with our guest, Dr. Emma Louise Spanswick. If you want to get connected with us to hear about even more amazing people doing science, listeners, follow us on Blue Sky at PBT Science, and I'm at PhD Marie. Now, we have another great conversation on the way from today's guest, so get ready to meet another one of our brilliant people behind the science.
Every day, discoveries are made that will change our understanding of the world around us. Dr. Marie McNeely is here to bring you the brilliant minds who are making these discoveries so they can share their incredible stories and take you on an amazing journey. Welcome to People Behind the Science.
Hello, everyone, and welcome to People Behind the Science. Today, I am excited to be speaking with our guest scientist, Dr. Emma Louise Spanswick. So, Emma, welcome to the show today. How are you?
I'm doing very well, thank you.
Well, I am so excited to have you with us today, and I'm looking forward to learning more about you and the work that you do. But let me give our listeners just a little bit of background about you and how you got to where you are today. Listeners, Emma is an associate professor and a Natural Sciences and Engineering Research Council Tier 2 Canada Research Chair in Geospace Dynamics and Space Plasma Physics in the Department of Physics and Astronomy at the University of Calgary. She completed her undergraduate studies in physics and was awarded her PhD in physics from the University of Calgary as well. Next, she worked as a visiting scientist at the Los Alamos National Laboratory. Afterwards, Emma returned to the University of Calgary as a research scientist and subsequently the Associate Director of the Auroral Imaging Group before joining the faculty there in 2019. Now, Emma was among researchers who received the 2018 Robert H. Goddard Award for Exceptional Achievement in Science from NASA, and she has been named among Avenue Magazine Calgary's Top 40 Under 40. And Emma, today we're excited to get to know more about you as a scientist, but also more about you in general. So can you tell us, what do you like to do when you're not doing science?
That's a complicated answer because I have two young children, two boys, ages now 14 and 8. So a lot of my time is spent with my boys and family, hiking in the mountains. Mountain biking is one of their favorite things to do. So I would say a large fraction of my time is spent with the kids and dealing with that home life balance. On my own time, I recently got into boxing. So that's a great stress relief if anybody's looking for a stress relief. So boxing and hitting the gym and in general, relieving the stress.
I think that is amazing. And I must ask, I think you're the only person I met who's sort of a casual boxer, if you will. How did you get into it?
I actually started with the virtual boxing. So you've seen the MetaQuest or whatever it is, and they have those apps for the virtual boxing. And I just fell in love with the cardio aspect of it and then started actually going to a boxing gym. And I wouldn't trade it for anything now.
Oh, I think that's so cool. And I love to hear that you're able to get outside and enjoy the outdoors with your family. I think that is a good way to de-stress and clear the mind as well.
Absolutely, especially with two boys. I swear they're powered by little nuclear reactors. So getting outside is a must.
Yes, burn off some of that energy.
Right.
Well, in terms of how you spend your energy when you're at work, how do you describe what you do, Emma, to someone who's not in your particular field or perhaps not in science at all?
So to start with, I'm an associate professor, which means I do teach physics in the physics department here. So that is part of my job. But as you mentioned, I'm a research chair. So I have a very large and dynamic research program. I'm a space physicist by training, which sounds very complicated. But what it means is that we study the Earth's natural space environment, which is connected to our upper atmosphere. It's basically seamlessly connected to our upper atmosphere and extends into the region around the Earth, where the plasma dynamics control essentially the motions of particles and things that we would like to refer to as space weather for the most part. But it's the region of space that's easily accessible by satellites and, to be honest, humans right now in low Earth orbit. So we study that environment and the interplay between the processes, so particle energization and particle loss from that system. So you'll find a lot of what I do in my daily job here is I work at the topic of space remote sensing is what we call it. So not only do we do the physics or study the physics or the dynamics of the space environment, we work in the space weather area. So we're looking for the technological impacts of the space environment. And then the third part of my program is actually working on those sensing technologies and designing instrumentation and field deploying the instrumentation to remote sense that environment. And so I kind of have this three-pronged program that goes all the way from discovery-based science through to basically sitting at the border with engineering in designing and building instrumentation that will help further the data that we have about the space environment.
Well, Emma, I think this is so cool, and I look forward to getting into some of the details of your work as we go through our conversation today. But perhaps we can pause to talk about motivation. I think we touched on balance earlier. It can be tough to juggle all these different hats that you wear in everyday life, and sometimes it can help to have a little quote or a saying or just something to motivate you and keep you inspired. So do you have one that you could share with us today?
Anyone who works with me, and it's sort of a medium-sized research group that I have here, knows that when we get down into it and we're discouraged or we're struggling with some of the technical challenges or the science challenges, that I will always pause and I will tell everybody, now is the time to go big or go home. And everybody starts laughing at me in the group because that's how we make those decisions to take that step, that high risk, high reward kind of decision. And that's the thing that motivates people around here, is that we've seen the successes come from those high risk, high reward situations. We've taken the risks, they've worked out. We've had some failures, but we've become really good at finding the areas where we know that we can take that leap. And I think the team around here, we all look for those moments and we just get excited when we see them coming.
Well, it sounds like you have an outstanding team dynamic. And I think it's helpful, like you said, to have this little rally cry, I think, for the team to keep pushing through these tough times. But let's talk about your role models and mentors. I think in science, these people can also help you get through the tough times. So when you look at your own career, Emma, are there people who really had a big impact on you as role models or mentors or just influential figures that you looked up to?
It starts in high school, right? Like, it's one of these things where if you would have told me as a high school student that you're going to end up being a professor in space physics, I would have laughed, because I came from a family of medical doctors, believe it or not. But I came through a school system where I had this just awe-inspiring physics teacher. And I can remember, I still play this video in my mind to this day of going home to talk to my parents. And I said to my mom, I said, Mom, I think I want to go into physics. And she gives me the mom look, right? And she just gives me this, the family of medical doctors. And I was like, okay, I'll let this sit for a little bit. And then I go to school and I come home the next day, the very next day. And there's a book sitting and waiting for me at my place at the dinner table. And it's called How to Get into Medical School. And at that point, I was like, oh boy, here we go. But in the end, everybody was supportive. I went into physics because of my high school physics teacher. And then you wind up in the physics program here. I went to the University of Calgary for my undergraduate. And I was just, it's one of those things where if you're having fun, you keep going. And I ended up by chance coming across a professor here in the space physics within the department. I came across him in the hallway and I just happened to say I was looking for a summer job. And he didn't even blink. He just said, you're hired. And that's how it all started, was a very quick hallway discussion. And all of a sudden I had a summer job working in space physics. And I can tell you from the second I started, I was hooked. It was just fascinating. The mix and match of the programming aspect, computer programming with the data, large volume data analysis, connecting to the space environment and remote sensing space processes. It was just so inspiring from the start. And as I got into the field deeper, like starting my master's and then into my PhD, when you go to these conferences, I found space physics to be one of the most supportive and welcoming environments. You hear stories as an undergraduate of these research fields that are very closed off and very competitive. But space physics is not like that. I found that I was a student giving a poster presentation, and I've got senior profs whom you look up to in the field, and they're all coming around to see your poster, and they're all encouraging you. It was just such a supportive environment that I have loved this environment ever since. And now I'm one of those profs who goes around, right, and supports the posters. And I just love it. It's a great field to be in.
I think that's wonderful. And I think it points to almost a little bit of serendipity. Like you mentioned that moment where you were like, I'm looking for a summer job, and boom, then you had it.
It's one of those things where the dominoes just fell into place. And it was pure fluke to run into the prof in the hallway.
Well, it's great to get some insight into how you got interested in science and how you started your path in this field. But what were then some of the key moments that really helped you get to where you are today? We mentioned as an associate professor and a research chair.
So key moments along my development, I would say, as you come through your master's degree, you never really feel like you know enough in the field, right? You're still learning and learning. And then you get to this point in your PhD where you're starting to have, not arguments, but friendly discussions about topics with your supervisor and with others in the field. And you're advanced enough in your knowledge that now you're starting to meaningfully contribute to those discussions. And I can remember a point in my PhD, I was actually in the first year of my PhD, when I was having a conversation. We were out at a conference and my supervisor and I are sitting around. We're just having a conversation. And I offhand had said, I think I can identify this one phenomena in this instrument by doing this. And I can remember the look on his face. He's like, I don't think so. And I was like, no, I'm sure of it. And then we went off and kind of dropped it. And then it would have been maybe 3 or 4 months later. He called me at home because there was an opportunity for a conference. And he's like, you remember you said you thought you could identify this process? And I was like, yes. And he goes, okay, do it. And that moment right there, I was like, all right, game on, basically. So I spent 4 months just engrossed in this data. And it turned out I was right after all. And it became the foundational paper of my PhD and what I started to be known for around the field. So that for me was like this pivotal moment where I had developed enough intuition to meaningfully contribute and I had the skills to follow it through. I think it was a pivotal point in my career.
Definitely. And I love to hear these stories where the professor sort of had that belief in you, or your advisor was just like, okay, I trust you. I'm going to let you try this. And I think that freedom can be amazingly transformative for scientists to be able to explore these things, to try these things that you maybe have these suspicions or hypotheses about.
Absolutely. And that's part of what I love about our field. People are supportive of you when you try to go out on a limb. They might not agree with it, but it's never an argument in our field. It's always just these friendly discussions of, well, maybe that won't work because of this. And then you can have other conversations. Well, I think it will because of this. And they're, okay, great. We'll wait to see the data. This will be wonderful. It's a very supportive environment for that type of basically curiosity.
Well, I think that's wonderful. And I think as you're developing in your research career, there's these sort of transition points. And I think as you're nearing the end of your PhD, this is a point where you have to start making some pretty important decisions. So for you, as you were getting ready to graduate, how did you decide what you wanted to do next?
All the way along in my career, from my undergraduate projects to my master's to my PhD, I feel like I was just going with the flow. And in reality, I was just following where I was having fun. It's one of those things where you start to find a problem really intriguing and you know you can meaningfully contribute to it. And it just keeps pushing you forward and forward and forward. And I've never fought that. I've always just gone with it. And that's basically what took me to where I'm sitting today, following those areas and that drive to contribute in areas where I'm actually interested in the outcomes.
I love that. And I know you spent some time after you graduated at Los Alamos National Lab as a visiting scientist. Can you talk about what the experience was like there?
That was wonderful. So I had known the people that I was working with at Los Alamos. I had known them from my PhD. They had worked with me on that paper that I had talked about, which was the pivotal moment. They had contributed to that paper, helping me with the data for that analysis. So I knew going in that I had aligned really well with what Los Alamos was studying at the time. And I just had the time of my life going down there. It's great to experience another lab, the different personalities, how they do things. It was just fantastic. And living down in a place like Los Alamos is just awe-inspiring.
Definitely. And then how did you decide to ultimately return to the University of Calgary to continue your career next steps?
Well, there were a number of factors. I was married at the time. So moving down to Los Alamos, we still had our house and my husband still works here in Alberta. And so he stayed working in Alberta while I moved south 6 months.
Mm-hmm.
When we did the long distance, basically I took the dog and moved south. It was a little difficult to manage that. So I knew I was coming back because of family reasons. And the timing just kind of worked out. It was essentially family timing that had me coming back. And also, I would say some of the opportunities here at the University of Calgary, I was still trying to contribute to the direction of the group here while I was at Los Alamos, still helping with some of the development in my spare time, knowing that I was going to be coming back into this group and wanted to make sure that the opportunities still existed when I came back.
Definitely. It sounds like you had a strategy going into it, perhaps whether you were aware of it or not at the time.
I think that's safe to say.
Well, it sounds like you're doing some remarkable research. I know you've been able to work on some really exciting projects over the years. Is there one in particular that you are working on right now that you are just the most excited about and want to share with us today?
We had that Nature paper that came out recently, and that to me really is a story about the go big or go home philosophy that we have. Because that paper, if people have seen it, it talks about the idea of this, what we call structured continuum emission. And it's very different than the aurora. The aurora, when you see the aurora, what you're seeing are the effects of basically particle impact in the upper atmosphere. And the idea that you impact some of the atmospheric constituents, right? And as you hit them, they glow, and they glow at specific wavelengths depending on the atomic or molecular transitions that you're exciting. For example, that's why the aurora is predominantly green, because you're hitting the 5577 angstrom oxygen line. But a continuum emission is very different. A continuum emission means you have elevated the amount of light in all areas of the spectrum. So it's no longer these discrete emission lines that we study when we look at the aurora. You've got this elevation of the spectrum altogether. And that comes from a completely different process. It comes from heating of the upper atmosphere. Essentially, you've heated it enough that it glows. And this latest paper that came out, we were able to see with some of our new technologies, and I'll tell the story behind that in a second, but with new technologies, we were able to pick out this kind of grayish, whitish toned structure, which appeared to be connected to the aurora. And it was one of those moments where, seriously, we were monitoring these new instruments, looking at the data coming in every night. And one of my senior techs here, I was walking into the office one morning and he yells, Emma, come here. And I look at his screen and he goes, something weird happened. And I'm looking over his shoulder at the data. And immediately I was just, what is that? And he's like, I don't know either, but it lasts here. And so he took the movie from one of our cameras. He kind of put it in a folder. And then I'm walking in a couple of days later and he's, Emma, it happened again. And I'm like, what? And so I'm looking over his shoulder and it happened again, but it looks a little differently. And then by the third or fourth time this was happening, I was starting to get a little bit worried. I'm like, okay, what is this that we have missed before? So we started to dig deeper into the data, and then we were digging in with full spectrum data that gave us a glimpse into the actual spectral content, which is what told us it was a continuum emission as opposed to these line emissions. And then we were able to find out that this kind of continuum structure, as you do in science, you dig deeper into the literature. You keep going back and back and back to see if you can find evidence of what you're looking at. And we found some very old evidence that had said these were unexplained emissions. And it came from a time when the technologies were very different than what we have now, where they were looking at only the spectrum. They were not imaging the sky, so looking at the structures. They just had information from the spectrum. And they had this data in the 70s, early 70s, late 60s, where they had seen this rise in all wavelengths at the same time, kind of connected to where the aurora was. And they could see the aurora based on the spectrum. And they called these unexplained emissions. And then we followed it forward and we realized very quickly that we were the first people to be able to actually take an image of what these structures looked like and how they were moving and how they were connected to the aurora. So that's this paper that just came out. But what it comes from at its core is the fact that the technologies are so different now than they were in the 70s. And the huge part for me is that we were a part of that development of these imaging capacities as we came along, because the camera that we were using to look at these patches of whitish, grayish structures were our recently designed cameras that we had literally said the words, go big or go home, when we were designing it. Because the design came about from a non-traditional way. We built the camera. It was not built like we would normally build a scientific camera for the aurora. It came from a time when I did a reset on our design process because what was coming out of our design process was not, I would say, compelling. And so I did a reset. I started looking around and I found a random article on a photography website that talked about a new Canon detector that had a effective ISO of 2 million. And I was staring at movies from this camera that were taken from a safari park where they were doing nighttime imaging of elephants. And they were showing the old technology where you get the gray, grainy images of nighttime photography in movies. And they were showing this image in this movie that was in full color at night. And in the back of my head, all I could think of was, I wonder if I could make that work. And that was the point. I cold called Canon Canada, and within 48 hours, I had a detector sitting on my desk that they had sent me to test. I configured it as an Auroral camera. I was in my pajamas in my front room pointing it north one night at 2 a.m. And I'm looking out my window and I can see barely any gray structures. It might have been cloud. And then I look through at the data that's coming from the camera and it's full of green and red. And immediately I'm like, oh, we can make this work. So we started the process. And that's the camera that eventually became the thing that allowed us to see this grayish, whitish toned structure. So for me, it's full circle. It came from our innovation in the detector space all the way through to basically a rediscovery of this structured continuum emission.
Well, I think, Emma, that is such an exciting discovery. And I think just in general, I feel like there's been a lot of public interest and excitement about the aurora over the past year or so. So how has this experience been like for you, being able to work on such an exciting project and having such a big breakthrough on something that's kind of having its public moment as well?
I will say it's been exciting for me because what's happened is our technology and our sensors that we've been getting into the field have been coming online. The data is coming in right as solar max is hitting. And that's the maximum in the solar cycle where we expect to see it's the most energy coming off of the sun. And we anticipate having more and more geomagnetic storms. So therefore the aurora at lower latitudes and things like that. And for me, one of these things of having all this data coming in has been the involvement of the students. We hire a lot of students around here. And for me, this particular study that we're talking about, one of the bright points of this study is that there are 3 students on that Nature paper. One of them is third author. He's an undergraduate student. So it's this new data and the fact that it was a what is that moment. It's not some detailed plasma physics discovery that only 12 people in the world will ever understand. It really was a true, oh my, what is that? And that made it completely accessible for students to meaningfully contribute. Because at that point, we're going from scratch. So we've had Josh Houghton, who is third author on the paper, and there were 2 other students, Christian Keenan and Jasmine Rosehart, also involved. And so it's been an entirely accessible scientific avenue. And watching those students engage with it, to me, it's the best part of my job.
Well, Emma, I must say that's going to be a tough act to follow for these students who are maybe moving on to their next project someday in the future. But I think this is so exciting. But I think in science, you don't have these amazing discoveries every day. A lot of it is just working through challenges, troubleshooting. And I think oftentimes you have these days where it just feels like everything is failing and going wrong. So for you, do you have an example of something you really struggled with in your career or just a major failure you had that you could tell us about and maybe share how you worked through that tough time?
There are so many. So anybody going through their master's and their PhD, I can remember days when I was troubleshooting my data analysis code and I would leave at the end of the day and the code would be in worse shape than when I started. And that was just demoralizing. It was like you come in and you're like, okay, I found one problem. I'm going to fix that problem. But by fixing that problem, I created 10 others. And those problems, I mean, they don't even stop for me now. I have those moments even now as a more senior scientist. So those happen all the time. One of those moments when we're talking about that camera that we were designing, prior to me taking a reset on that camera technology, we had gone a year or so in development and come up with nothing viable. I mean, we had designs, they would take data, but it was just those moments where nothing we're doing is producing the kind of results I want to see. And this happens to me all the time in instrument development. And so we keep taking those resets and steps back. And honestly, it's a part of the process. And it's a part of the process I tell the students about. All of my graduate students who come through, we call it the grind. I tell them there will be a grind. There's no way around it. No one's research is a straight line path from A to B. We're taking detours. We know we're taking detours. We know we're going to go backwards. So we just have to grind it through because that's how we learn and that's how we get the results.
Definitely. And just to give our listeners some context, how much time did this particular example of sort of the technical grind with this camera take?
We were grinding in the wrong direction for at least a year.
Oh, gosh.
And then once we had the revelation of we want to use this camera, it was, of course, it's not designed to be a scientific instrument. It's designed to be a movie camera.
Right.
So then became all of the technical challenges surrounding that. And we were probably about another year in development from that before we were ready to take our first test images with a prototype. So it was a 2-year grind to be able to get to where we needed to be.
You're really invested, I think, by that point. So,
oh, yeah.
Well, wonderful to hear about one of these difficult times. And it sounds like just the persistence was key, just continuing to go in every day and trying to make progress on it. And I think that's something you see across all fields in science, and an important lesson for early career scientists to learn that you're not going to have one of these wins every day. There will be a lot of days where you do not win, and sometimes where you even kind of move backwards. But I think it's all part of the process. And we love to celebrate the successes in science because sometimes it is a difficult time and a long drought between the successes. But do you have a favorite one? We mentioned this Nature paper earlier, of course. Is there another success story you'd like to share with us today, whether it was a big win or just a small but particularly meaningful one?
When we make these little wins with the camera becoming, for example, the best camera that we've ever imaged with in terms of the true color space and the dynamics, and the other successes we've had on the instrumentation, they serve to set you up for those big opportunities. And to me, the big successes that we've had in this group is being able to identify those big opportunities and take advantage of them. So for me, one of the huge wins that we've had is the recent grant that we were awarded for Geospace Dynamics Constellation Ground. It's a very large Canada Foundation for Innovation Fund grant. So it's a $15 million total project cost. The idea behind that grant is to revamp the infrastructure across Canada that we operate. So it gives us an opportunity to advance the technologies that we have currently for looking at the space environment to the next level. And we're doing that right now to advantage ourselves for some of the NASA satellite missions that are coming up. So we want to be able to have the best ground data possible while NASA is taking the best space data possible. And the combination of the two is what will allow for some of those breakthroughs in science. And so for me, these big wins, like winning that grant, has been huge for us because it's a vote of confidence in our capacity to develop the instrumentation and deliver on the science, right? So the international community and the Canadian funding system has seen that we can deliver. So to me, that is one of the huge successes, is that we've taken these little discrete packets of success, right? And we've built them into these larger opportunities where we can really start to level everything up and open the door for some of these more discoveries like the continuum mission.
Very interesting. And do you have an example of maybe something that you want to measure or that you're hoping to measure with these upgrade or advances that you're not able to measure with the current infrastructure?
Like so many things, we struggle with the fact that when we're imaging the aurora and we're working in some of these narrow wavelengths that are these emission bands of the aurora, we're photon starved. So the data we have right now, if I show people the data from some of these narrowband imagers, it looks very, very noisy. The signal to noise ratio is very low. So some of the advances that we're working on now are how do we increase that SNR? How do we decrease the detection threshold so we can see the dimmer emissions? Because we're starting to understand through some of these other cameras that the neutral atmosphere and the space environment are coupled way more than we had previously thought. There's feedbacks in there. The neutral atmosphere is feeding up into the ionosphere. The ionosphere is feeding information down. So as we start to develop these newer technologies, I'm hoping that we can start to tease more information about the connections in the space environment that we can't see right now because we just don't have the sensitivity, or we don't have the time resolution or the spatial resolution. So by upping our game essentially on these three fronts, I'm hoping that we start to see the unseen.
I think that is a lot to look forward to. Over what time frame will this grant be executed?
Well, we're in the initial stages at the moment. And I think over the next 4 years, we're going to start to see the instrumentation start to come out. We're hoping for some prototypes to be done in the next year. And then we would start full-scale deployment probably in years 3 and 4. That would end up being in about 2028 through 2029 with full network out there.
Oh, wow. And you mentioned, of course, locations across Canada. How many locations are there? How many places are going to get this upgraded equipment?
It is exceptional. So I remember writing the grant, and I have US partners on the grant, and I had written in the grant that we were going to deploy instrumentation coast to coast to coast. And I remember a US partner writing back, and she wrote back, she goes, "I think you mean coast to coast." And I was like, "No, I don't. I mean coast to coast to coast because there's the Arctic coast in there." And she was shy about it. But we are looking at something like 27 locations all the way across Canada, covering from the West Coast to the East Coast of Canada and all the way up as north as Eureka.
Wow.
And so when we look at that on a map, it kind of makes a piece of pie that is the Canadian sector, as we call it. And our goal is to cover the complete Canadian sector with instrumentation. So we would have a more complete picture of the space environment across different regions than we've ever had before.
Well, Emma, this is absolutely thrilling. We look forward to hearing more about this project as it evolves over time. Listeners, we're going to have to keep an eye on this one. I think these successes, these moments of jubilation in science, when you get that grant, when you make this big discovery, they can motivate you to dig in deeper and keep asking questions and keep working harder and harder and harder. But we try to encourage our listeners to take a break, to take a step back, try to read for fun, broaden your mind. So do you have recommendations for our listeners of books that you've really enjoyed that someone can pick up if they need a break from the lab?
I spend most of my time, I will say, if I'm resetting from the lab, I spend it on the stair machine trying to make my mind blank as possible before I come back. So I don't think I would have any recommendations on that front, unfortunately.
Gotcha. Well, how about books that you would recommend for maybe undergraduate students about science or things that they could learn, life lessons that they could apply for their careers and their lives?
I got all my life lessons firsthand, unfortunately, by shooting myself in the foot doing things. In terms of the content for undergraduates, I mean, not from the book sense, but if you're looking to engage, I would say with space physics, there's lots of online content now that you can have access to because we've seen a rise in interest in the space environment that comes from a couple of reasons. I mean, partly the solar cycle and the fact that more and more people are seeing the aurora. More and more people are able to image the aurora with cell phones and things like that. So that's raising interest in the field. But we're also noticing an increased interest in the field when we start to see the technologies that are impacted by the space environment. So you'll see articles on GPS or global navigation systems outages because of space weather. So there's lots of content popping up online and lots of social groups. The Alberta Aurora Chasers are one that our group keeps in touch with frequently that post neat articles when they find them about space weather and space science. And the other area I point students to all the time, my undergraduate students, I point them at the national space agencies that have a lot of material designed for ranging from elementary school children all the way up to media content. So you'll find NASA's website on space weather or heliophysics as they call it, or you'll find the European Space Agency has a very large space weather presence. Even the Canadian Space Agency has content. So you can find lots of those little articles that will give you the nuggets of information. I like the bite-sized chunks myself. When I'm learning about a new field, I don't tend to dive in so deep. I like I call it tip of the iceberg when I'm talking to my students. Like, learn about the tip of the iceberg before you go underneath and see how far it goes.
Right.
But that kind of tip of the iceberg information you can find quite easily these days on the web with our field.
Perfect. Well, I think these resources are great. Like you said, sometimes you don't want the full textbook. You just kind of want the little highlights, the things that'll capture people's attention and help people decide what they're most interested in. So we appreciate you sharing those resources. And I think one of the things that we haven't had a chance to talk much about in your career are opportunities for travel. I think this is a big part of life as a scientist, whether you're working with collaborators all over the world or just going to different conferences, working with colleagues. So do you have a favorite place that your science has taken you, Emma?
I've had the opportunity, because space physics is very international and we collaborate. It's a tight-knit community, as I said before, a tight-knit and supportive community. So there's tons of opportunity to travel. I was in Madrid a few months ago, heading out to Switzerland later this year. And that's scientific style travel. I mean, lots of opportunities in the US to visit NASA Goddard Space Flight Center, national meetings in San Francisco. And they're all wonderful places when you've got those wonderful collaborators. For my specific job, we also have the field work, right? Because we're deploying these instruments to the remote north. So while not a favorite location of mine, Resolute Bay in Nunavut is the farthest north that personally I've gone. I can't count the number of times I've been there now. And I hope there's nobody from Resolute Bay listening, but I actually hope to never go back to Resolute Bay. So the travel up north can be fun, and seeing the different locations in the north is definitely a cultural experience. And then there's the more common science travel, conferences, and just collaborative visits that are abundant, I would say, in space physics because of the collaborative nature of our field.
Very cool. And you mentioned Madrid specifically. Perhaps we'll hone in on this trip. You mentioned it was relatively recent. What was the occasion for going there?
That was a workshop or a conference on data and software in heliophysics.
Ooh.
So it's strange when you think I'm in the physics department, but space physics itself is very, very multidisciplinary. And when we go to these international conferences, people who are in the space physics or space weather fields can come from physics. There are some who come from geophysics departments. There are a lot who come from electrical engineering departments. So what you got is this really multidisciplinary environment, and it's an environment that's very heavily dependent on instrumentation that's running either on, spacecraft or things like this or ground systems, and a ton of data. Our field is very, very data driven. So the Madrid meeting itself was a data and software and heliophysics, and I was invited to give a keynote on the challenges and triumphs of building one of our most recent networks in terms of the software. So it was speaking to a lot of people who understand the intricacies of handling big data, archiving big data, how do you access it, the machine learning frameworks that are layered over top, and then also those instrumentation pieces of autonomous systems, right? How do you manage the software systems for these autonomous instrumentation that is across the north? And so I was speaking largely to a group of people who were very interested in the software and the data for that instance. And it was a fantastic visit. It was held at the European Space Agency. So it was great.
Very cool. So were you able to explore Madrid a bit while you were there?
Actually, I did. We took the opportunity to go to 2 football games while we were there, and then was able to sneak off for one afternoon and see the Prado.
That's amazing.
So you do take the time while you do it. You try to sneak off for half a day if you can.
Oh, absolutely. I think it's part of the cultural exchange too, getting to kind of understand the historic sites and the culture of the people in this place that you're visiting. So I think these opportunities are remarkable in science. And I think, as you've hinted a couple times throughout our conversation, just the people you get to work with are amazing. And it sounds like this is particularly true in your field, where they don't necessarily fit that stereotypical view that people may have of a scientist being grumpy with crazy hair working by themselves in a lab. So if you had to share with us perhaps one of these human moments in science, whether it was a funny memory that you shared with colleagues or just a quirky tradition that you experienced in one of the labs, do you have an example that goes against these stereotypes?
I do. So in all fields, there will be those grumpy scientists. And I have a vivid memory. So this happened to me as a student. I was a master's student at the time. I was in northern Finland at a meeting, and the session was being chaired by one of the, you call them the bigwigs in the field. And he was chairing the session, and I had given my talk. And one of these grumpy old scientists had come up and started asking me questions. And essentially, he was just lobbing really hard questions and making it seem like my research was nothing, basically. He was tearing me down. And the bigwig who was chairing the session not only stopped him from talking, but then, as a panicked student who's sitting there like deer in the headlights, he looks at me and he starts throwing me softball questions. And so he brought me back. So I answered these questions and done my talk. And, as a student, you just basically got shredded on the international stage. So I'm sitting in a chair, my head in my hands. And another bigwig whom I hadn't met at the time, but he knew of me and I definitely knew of him. He's one of those people where you see him in the room, you're like, oh my God, oh my God, oh my God.
Right.
And he came and he sat down beside me and he gave me a half an hour pep talk about how great my research was and how this had happened to him when he was early in his career. And he talked about how it happened to him and what he did about it and how he persevered through it. And then he proceeded to build me up. And it was one of those very human moments where I was like, all right, this field is really, really supportive, because I've got these 2 bigwigs, 2 of the biggest names in our field, helping me through this situation, telling me that it's not normal that this guy did this and it's not okay that he did it, and then building my confidence back up. And so from a moment that could have been very devastating to a young scientist, I came out of that energized. To me, that was one of those kind of pivotal moments, again, in my career.
Absolutely. And I think having those people in your corner can make all the difference. Someone could feel disappointed and upset and sort of that imposter syndrome creep in after an experience like that. But to know that there are other people that are now very successful who that also happened to, I think can also change how you think about it.
Exactly. And I can confirm the imposter syndrome never goes away.
Well, something to look forward to, listeners. But I think it's great to hear these moments that go contrary to people's stereotypes of scientists. There are some wonderful people out there doing science, and I think in most cases they are the majority in a field. And I think you work together to answer some really difficult questions, but oftentimes you're limited, unfortunately, Emma, by things like funding, staff, technology, feasibility, these little details like time. So if we took away all of these barriers that normally hold you back, is there one research question in particular that you would want to answer most?
Oh, they're all interwoven. So the problem is, for me, this whole system is a system of subsystems, if you catch my drift. And at any given time, we're studying one of the subsystems. Like for me, for example, I like to concentrate on the high energy electron population. But there's a high energy ion population. There's a low energy electron population, right? There's the ionospheric feedback. There's all of these things. So to me, the real problem is, how does this all fit together? How can I take something that I'm working on and fit it into people who are studying the details of ionospheric and neutral chemistry models? And the idea of trying to tackle that is kind of mind-blowing. So if we removed all barriers, I would hope we could get to a point where we're able to better integrate the modeling that we have, the different models, as we model different areas of the system differently. So integrating the models and the data to try to understand and kind of elucidate those connections between the subsystems and how that coupling really works.
I think that's wonderful. And I think that's a problem that can apply to a lot of scientific fields, right? I think in many cases, science are studying this one very specific problem that exists within a broader system. So being able to take a step back and really understand and see the bigger picture and how all of these pieces connect and influence each other and work together, I think is definitely a big challenge, something that everyone's sort of chipping away at their different pieces to. But I think that is an amazing answer to this question of what you would spend these unlimited resources on.
Yeah, it's definitely not unique to space physics. I mean, I always think of medicine, right? Some people studying the different systems within the body, right? And then realizing that this system interacts with that system. And it's one of these cases where every time we look, we find that it's more complex than we thought. And at some point, we need to solve it.
For now, it's job security, right?
Yeah, for now.
Well, Emma, I think that is wonderful. Thank you so much for giving us this big problem to ponder today. And we'd love to wrap up by talking about advice. So for you, was there one piece of advice that somebody gave you at some point in your career that really helped you that you can share with listeners out there today?
I can. And actually, the advice came from my supervisor and also my father. So both of them, in different ways, had said to keep doing what you enjoy. And if you're having fun, you're in the right field. So my advice would be to try and find that area to any of these young scientists, find the area that the problems really stick with you. They bug you. You want to solve them. And it's fun to engage with those problems, because if you're doing it that way and you're following where you're enjoying yourself, your job won't be a job. It will just be fun.
Well, I love that advice. And it sounds like I'm so glad that you ignored that med school prep book from way back in the day. So is there any other last piece of advice or a last note of inspiration that you want to leave everybody with today?
Everything that's come out of what we have done has just been, as you said before, right? Tenacity. I mean, my husband calls it my stubbornness, but the tenacity to just keep going, especially if you're having fun, you just keep at it, because when you think that it's not going your way, there will be a turning point. And that has always happened with us. There will be a turning point.
Well, I think that's really helpful to hear you say. And for our listeners who want to learn more about you and more about the kind of work that you're doing, what is the best way for them to do so?
Well, as I said before, it's probably the web. There's a lot of resources about space weather and space science on the web through those national agencies' websites. The U of C has some information up, or if people are interested, they can connect with me directly. The best way to reach me is usually via email. But yeah, definitely connect.
Excellent. Well, listeners, definitely take the time to learn more, get connected with Emma, and ask your questions if you have any. And Emma, thank you so much for spending time with all of us today. It's been a pleasure to chat with you.
Oh, this has been fantastic. Thank you.
Well, it's been great to learn more about you and your work. And listeners, wonderful to have you here with us for the ride. We hope you join us again next time for another episode of People Behind the Science.